game session. And actually, I find all sessions in CIG very interesting and attractive, but personally, I prefer this one. I find it's the most attractive one. And just half hour ago, I almost had a fight with Simon. We argue about which session is more interesting, this one or the next one. I think he stayed there is just because he thinks I may win in this competition. Well, it's like the game playing right. Each person has a different definition of fun and enjoyable and the preference of game and sessions. So, well, I think I've taken too much time, sorry. So let's welcome our first speaker, Alberto. Our first speaker, Alberto Uriarte. Thank you. I practiced 10 times.
So, hello everybody. As you said, my name is Alberto Uriarte, and I'm going to present a paper that we did with Santiago and Tañón about a single belief state generation for partial RTS games. So we have RTS games that these kind of games are really, really complex, and the search space of these games is insane huge. So most of the approaches using are search-based approaches are really hard to deal with this search space that is so big. Some nasty tricks that have been done previously in years are making a portfolio to limit the search in some areas, or making another kind of game with abstracting the game state and searching on this abstract game. But none of this previous work has deal with the fog of war, because if we want to deal with uncertainty, we're going to increase the search space. So if we are not able to search in the current game state that we are seeing, how are we going to search what we cannot see either, and it's going to be bigger and bigger? Well, we're going to try to do it. So our goal is to handle imperfect information in the kind of games. Most approaches requires to explore the whole game tree. That's going to be impossible in our case. Other approaches try to generate belief states and explore these belief states. In our case, this is still really hard to do, because to maintain and generate these belief states is going to be huge, so we cannot explore all of them. Then we try to generate a single belief state from previous observation and inference, and then use determinization. So in RTS games, usually the process to play these games is we have the game state, that we have immediate information of the game state. We analyze this and we can infer some information. So if we see a flying unit somewhere in the map, it should be an airport. With this information, we can anticipate our opponent's moves. And then with all of this is the game state, we can planify a strategy. That's a long-term plan that we want to execute. With this strategy, we have the tactics that are short or medium-term plans that we can to execute. And then finally, we execute the individual orders to individual units to execute our plans. With this execution, we will have another immediate information of the game, and we keep going this circle many times. So with this immediate information and with this inferred information, we're going to create our game state to do search on this, and then command our army in the RTS games. And once we have this game state that we enhance with some information, we perform determinization. So the determinization only takes from an information set, that's all the game states that are not distinguishable for one player. We sample one of them, and we execute one game to search like we have full information. So the search still thinks that it has perfect information, and this has some drawbacks that some people have already proved, that one of them are strategy fusion. So players must behave the same way in states from the same information set. But it's not true when you're using determinization, because when we use determinization, we are assuming game states, and we are going to do actions depending on this game state that we are assuming. So different game states that belong to the same information set are going to have different behavior, when in fact they should have the same behavior. Other problem is non-locality. So the search can be full to pursue a state that has a higher reward, but the chance to get there from the information set are really, really low. So it's no sense to try to achieve this reward, because it's really hard to get. And there's another third one that we call fake omniscience. Since the search believes that it has full information or imperfect information, he will never try to hide or gather information because he will already think that I know everything that you have to know. So despite these drawbacks, there are some success using determinization, and some people analyze, okay, why this works in some games and other games doesn't work at all. So these people define 3 different properties. That it's leaf correlation, that is a probability of another terminal node with the same payoff value. Then bias, the probability that the games favor one particular player to the other. And a disambiguation factor, that is how quickly the states in an information set shrinks because of the depth of the tree. So with these properties, they analyzed some games, and they found why the determination works or when the determination is going to work. And it's when the games have a disambiguation factor very high, or the leaf correlation is very high and bias polarized. It means the bias can be really high or really low, but not in the middle. Okay, so we took these properties and we analyzed it in a micro RTS games in 2 different maps, one 8x8 map and one with 12x12 map. And we found these values. So for the leaf correlation, it's really high. So from the values between 0 and 1 is almost 1. So, and now we need a bias to be polarized for the determination to work here. But the bias is just in the middle, exactly, more or less. So 0.5 in most of the 2 different maps. Then we need now the disambiguation to be very high, but we found that disambiguation be 0 or in some cases negative. So instead of having here values between 0 and 1, we have values between -1 and 1. Why this? Well, RTS games have particular properties and other incomplete information games. In RTS games, we can make moves that are exposing us, so they are giving to our opponents information, and there are moves that we don't give any information to our opponents. And the other way around, our opponent can make moves that give us information or not. So having this, the information sets can grow and it shrinks, not only shrink, can grow. So if we lose a unit in the map, then we don't see that area of the map and we are losing information on that area. Okay. Another particularly interesting is that observing the disambiguation factor over time, we can observe how at the beginning we gain a lot of information when we send our units towards the enemy base, and then this information decreases because we already have all the information of the map. And in the case of the player that is losing, the red one, is losing information because it's losing units and doesn't see any part of the map anymore. So maybe we still have some hope if we see that we have a higher peak, almost reaching 1, that we can have a really high disambiguation factor. So we proposed 3 different single belief states. The first one we call gold seeker, that we only record the enemy buildings in the initial game state. That's similar to our overconfidence behavior in some papers. Then the imperfect memory, that is only the last known enemy unit location. So once the unit location is visible again and there is a unit, we forget that we have seen a unit there. And the last one is a perfect memory. So now we're gonna remember that we have seen an enemy, and if the location is visible again, we're gonna make an inference to see where is the most probable location that the units is now. On top of that, we added some inference mechanisms that if we see, for example, a melee unit, and we haven't seen barracks yet, we know that some place there's gonna be a barrack. We experimented with different AIs. The first 3 ones are hard-coded. So we have the random bias. It's a random AI that has a bias towards moving and attacking. Then we have this worker rush that's going to produce only workers and send it to attack to the enemy. And this light rush, that's the same as going to produce a barracks and then send light melee units to attack the opponents. Then we have a bunch of Monte Carlo tree search AIs. The first one is the canonical epsilon greedy Monte Carlo tree search that we call it blind because he only takes into account of the part of the map that he's watching. Then there are 3 single belief states that we are proposing. And lastly, another Monte Carlo search cheating because he has access to the whole game state, not only the parts that he can see. We tried with 4 different maps. The first 3 in the top are using only 1 base. So they are the most common maps for RTS games. And the bottom 3 are you start with 4 bases to see how the difference between the hard-coded approach and Monte Carlo tree search approaches behave in these scenarios. So the best part, the video time. Here we have a game from the micro RTS. In the top left is a blue player that is a single belief state with Monte Carlo search, and in the bottom right is a red player. It's hard-coded with light rush. So it's going to produce melee units and send it to the opponent. Since this is a partial separable game, only the squares that are in blue are accessible for the blue player, and the squares in red are accessible for the red player. And here we can also observe in purple, there's a square and a dot. This is the belief state of the Monte Carlo search single belief state that believes. So the squares, white squares are the bases, the greens are resources, the dots, the small dots are workers. So if we start the game, we see how both of them are making a barracks to produce new units. The purple, it doesn't move, even the worker is moving. And he doesn't know the blue that there are 2 melee on the bottom. He only knows the purple things that in the belief state there are. So they go directly to the enemy base and attack it, what he believed that was there. And the other now they can see that the blue tried to defeat it, but it's too late now. So in this case, for Monte Carlo search was able to win a hard-coded strategy. The interesting part as well is that even we didn't specify an algorithm to search or gather information. It has an emergent behavior to go to the last well-known unit position and try to find where it goes, that unit. So this is the results of the round-robin tournament between all the AIs. The first row are the maps, the small maps, and no, the first row are only with 1 base, and the second row is a map with 4 bases. So the first thing that here we can observe is the 3 first columns are the hard-coded strategy, and they perform pretty well in the maps with only 1 base, but in the cases with 4 bases, they perform less better than the Monte Carlo search approaches. So in the smaller maps, you see that the first column are the 8x8, the second the 10x10, and the third the 12x12. So in the 8x8, the worker rush defeated with the best one, because the map is so small that we don't have to wait to produce melee units. You can just go with the workers attack. But when the map gets bigger, it's better to produce a barracks and then the melee units to attack your opponents. Then the rest of the columns, we have with different number of playouts. So we give more computational time or budget to the Monte Carlo search. So as expected, if we give more computational time, they're going to perform better. So they are in groups of 3 with 100 playouts, 500 playouts, or 1,000 playouts. And the first 3 gray are the Monte Carlo search, the blind one that he can only see what is looking at. And the last one, the purple one, is the cheating one. So we have the boundaries. So the first one is the worst case scenario, and the last one, the cheating, is the best case scenario. And our belief states are improving over each other, not reaching the cheating, but getting really close to the cheating one. If we observe the difference between the score between the cheating one and the other ones, you can see that the known performs about 50% worse than the cheating. And the other, when we use a belief state, this improve, and we only lose between 20 or 10% of we are cheating in this case. If we analyze the similarity between the belief state and the real game state, in this chart we can see that 1 means that our belief state is exactly the game state. That's going to be impossible. And 0, that we have any idea. This doesn't match at all. So we can see a depression at the beginning, that this is at the beginning of the game until we send some unit to the opponent's base. We don't know what's happening there. So we have this losing information until we reach the enemy, and then we gain some information, and then the information decrease over time again. This is very interesting because here we can see clearly why professional players they perform scouting at the beginning of the game, because they want to avoid this depression. This not knowing information, it hurts you a lot because you want to counterattack your opponent's strategy. So the best thing that you can do is to prevent this thing is send someone there to get information as soon as possible and then react in the best way. As a bonus, that this is not in the paper that we submitted here, but we ran experiment in StarCraft. So in the blue line, that was our previous bot that it has access to the whole game state, so he was cheating. Once we remove the access to the whole game state, is the red one. So the win ratio decreases dramatically, and we incorporated again our belief state. The performance was very similar to the full stability bot. As a future work, we still not are hiding or gathering information with this approach, and the actions are durative, and we are not doing that. That means that if we have seen a barracks over time, this barracks are going to produce some units. We are not considering that there are new units are going to spawn there. We have to look for them as well. So that's it. If you have any question, thank you. Yeah.
I think it's really, really nice work, and I think the micro RTS game is really, really good for this sort of research. What wasn't clear to me, in micro RTS, how do you perform hiding as a player? You said it's one of the strategies is to perform actions which hide things, information hiding.
No, it doesn't perform any hiding actions. So
you say still not hiding information, but how would you in this game?
Well, in this game, you can hide information trying to prevent your opponent to reach your base, for instance. Then you are making...
Oh, by trying to stop the scouts.
Yes. That's, for example, one instance of how to prevent your opponent to gather some information from you. Or you can fake some information. You can let him see that you have a barracks, but in fact you are building some airports to launch an airstrike. So you can mislead information as well.
So how would you do that? How would you...
That's future work. So
okay.
Those are the next steps that we have to deal with this kind of approaches. Yeah.
Yeah. Okay. Thanks.
Any other questions? No. Well, shall we move on to the next speaker, please? Yep. Thank you. Thank you. Thanks for your presentation. So let's welcome the second speaker, Niels Ustisi. Thank you.
Thank you. I will present our paper, Learning Macro Management in StarCraft from Replays Using Deep Learning. So deep learning for game playing has achieved a lot of success in the recent years. We all know AlphaGo and the Atari game playing, learning just from raw pixels. It has also been demonstrated to play racing games and Doom as well. But what about more complex games than such as real-time strategy games? In these games we have to control a lot of units at the same time and in real time, and we have partially observable game states. So it's really difficult to apply these methods to such games. You might know some of these competitions. One of them is here. StarCraft has a lot of interest in the AI community. And when I made these slides, I counted 61 bots. I think there are more than 100 that are online available. But many of these bots, they have scripted procedures. They can only adapt to a set of predefined strategies or adjustments, at least most of them, and this makes them very predictable, especially for human players. This is an architecture in Alberta bot, one of the famous bots in the competitions, and it has this modular design. So it basically splits up all the subtasks in StarCraft and try to solve them individually. And in contrast, if we have a neural network, we would like to learn just to have one neural network. We take in the game state and we output some actions that we produce in the game. In Atari, this is fairly simple. We take the pixels from the video game, from the screen, and we output the actions in the controller. But it's a bit more complex in StarCraft. How would we actually take in the game state, and what are the actions? So it may be a bit of a naive approach to have this single neural network that can play the entire game. Instead, we could try to look to split the tasks into micromanagement and macromanagement. And in this case, we define macromanagement as the strategic planning of buildings, of which buildings, units, and upgrades to produce and in which order. And micromanagement is the tactical control of individual units and buildings. So in the experiments I will present here, we have tried to train a neural network to perform the macromanagement tasks. If we look at what they did with AlphaGo, we can make like a rough recipe. So first we apply supervised learning to learn from human game logs to kind of bootstrap our neural network. And this system is by itself able to play the game at a decent level. The next step is to improve the neural network with reinforcement learning by self-play, or it could be against other bots. And finally, it can be a search algorithm like MCTS can be added on top. So the neural networks acts as a heuristic or as an action sampling function. So again, we are only looking at the first step in this project. So our data set is from 2,000 replays, and from this we extracted almost 800,000 state action pairs, and this is kind of an abstract state description. So we try to describe the state as only material information in the game. What is the number of units, buildings, upgrades, and technologies that we have available, and also what we know about the enemy, which is only partial knowledge. And then we create a neural network where the input layer is this game state description. We have again our own material. We have material that is under construction. We have the progress of material under construction, and we have what we know about the opponent material. So the input layer is actually larger than we see in this simplified example. We have 210 input units, and we also input some information about the supply. In our network we have 4 hidden layers with 128 rectified linear units, and an output layer with 58 units with the submax activation function. So these 58 units, these are the different units, buildings, and upgrades that we can produce in the game. And the network will then learn to predict what would a human do in a specific game state. Just some details. We use the atom optimization algorithm and learning rate of 0.0001, batch size of 100, and the cross entropy loss function, which is usually used in the classification problems like object recognition and stuff like this. So using all the different parts in the input layer, we achieved an error rate, top one error rate of 54.6%, meaning that we on average can predict what a human player would do about half the time. And if we try to remove parts in the input layer, we see that the error rate increases, showing that all these informations are actually good information for the network. So this trained network we then put into the Alberta bot. So whenever the bot requests for a new build in the game, it asks the network to predict what a human would do, and then we produce that building or unit. So we designed two action selection methods. One is the greedy, and which I think also is the usual way of doing it. We take the output of the network with the highest probability. So if the network predicts that we should build a Dragoon unit with the highest probability, we will always select that unit. But one problem with this approach is that we will never select any upgrades, because upgrades are so rare in the game that the network would never predict an upgrade to be the most probable action in the game. So we also designed a probabilistic action selection method that simply selects a build using the probabilities in the softmax output units. So if the network predicts there is an 80% chance of producing the Dragoon unit, we could also produce some of the other units. So looking at what build orders the system actually produces in the game against the built-in Terran bot, we have this timeline with the number of frames in the game and the probability of producing each unit. So in the beginning, it always predicts to produce workers, and then later in the game, it will begin to predict other buildings, such as the pylon here, workers again, a barracks, a gateway, which is a barracks for the Protoss, and it will begin to mix the unit production. And the two action selection methods produce quite different unit numbers. We see that the greedy method here almost only produces Dragoons, while the probabilistic is more spread out. It also produces these Dark Templars and the Zealots, and are also able to produce some of the upgrades, in contrast to the greedy approach. So we tested these approaches against the built-in Terran bot and achieved a win percentage of 68%. We also tested the probabilistic approach by not giving it information about the opponent, just to see if it actually makes it predictions based on what it sees from the opponent. And we can see that the win rate is lowered a bit. And the greedy approach is not as good as the probabilistic. Taking random micromanagement actions never won a game, and this is random but legal actions. Alberta bot with a scripted rush strategy wins 100%. So in comparison, this is not as good, but it is a very promising approach, and I hope I can show you a video of this in the end. So some future work that could improve this approach. We could improve the other modules in the bot. For example, our network, as a human would do, really wants to expand many bases, wants to have a large army, and whenever it is in the lead, it would rather expand its base rather than rushing in the early game. But UL bot is not very good at managing multiple bases and multiple armies. So this could be improved in the bot. We could integrate positional information into the model, and in the new StarCraft 2 API by DeepMind, this is actually possible by having some simplified visual information. So at the moment, we are only looking at material information. We don't really care about where our units are positioned, and that can have a big influence in what kind of buildings we want to produce. We also want, of course, to train our network further with reinforcement learning, again with self-play, but it could also train against all the many bots that are available online and learn to beat those. I hope we have time to see some of this. I'll try to speed it up. Great. It's obviously more fun if you know the game. In the beginning, as I said, it only produces workers. Then it starts to build a pylon because it's out of supply. And it starts to scout, but this is not a part of the network that we trained. This is a part of the other modules in the bot. And it builds a gateway to produce combat units, and a simulator to gather gas. And now that we are scouting, these informations from the opponent goes into the network as well. And it starts to produce combat units, and maybe we can skip a bit. So at least when I watch this, it looks like a strategy that a human could do at this point. But watching many games, it does some variation because of the probabilistic approach that we see here. So in some cases it produces air units, and in other cases it produces only ground units. And I think this space of strategies that the network can express is a very good foundation for the reinforcement learning that we want to put on top. And it has expanded its base, so this area. And observing many of these games, it usually does this when it's in front. And again, the micromanagement is not part of the network. So you'll also notice that it has produced 2 of these advanced buildings that a human probably never would do. And this is because of the probabilistic approach, that it can actually select an action that is very rare. If we go to the end, the Protoss units produces invisible units, and the Terran is not able to respond to that. And it expands against because it's in the lead and wins the game. Oh. Yeah, thank you.
Hi, interesting work. So I have one comment and one question. So the comment is, if you think about the sampling as like sampling with a temperature, your probabilistic, greedy, and random are all just 3 special cases of different temperatures. So it might be interesting to like think about tweaking like how random and how determined, like how epsilon greedy or it is, to maybe there's like a sweet spot somewhere in between that it's not doing something completely random versus.
Thank you.
And then the other is, did you consider like treating it as like using any sort of like sequence-based things like an LSTM or something that like it might not like you said might not make sense to do 2 of those advanced buildings. If you had like the sequence of past actions, then you probably wouldn't repeat that again because it doesn't really make any sense. Is that something that you'll do in future work, or?
I thought about using a recurrent neural network, but some of the counter arguments would be that all the actions we take are usually present in the game state. If we build a gateway, it is there. And also, if we see some opponent units and they go out of vision, we actually save that in memory and still put it into the network.
Okay.
I have 2 questions. So the first one is for the input layer, and the second one is for the output layer. So for the input layer, do you consider the entity for the opponent material? Does it have to be a linear number? Can it be decimal number? As in, like, what if you scout and you see a construction, a building in construction? Is that a 1 or is that a 0?
That's a 1.
That's a 1.
Yeah, and all the numbers are normalized between 0 and 1.
Okay,
so yeah.
Also, for the output layer, so if how long do you wait till you take the next action? As in, like, okay, you decide to build a building, right? Do you wait for the building to be finished to take the next action, or because what if you scout and you see some new information and you want to revert to a different strategy? Do you keep with that strategy, or how do you change it?
Whenever an action is taken, so starting a building or start producing a unit, we ask the network again, what should we produce next?
Okay, and
then we keep waiting until the network or the bot is actually taking that action.
Okay.
But I agree that it could be optimized such that if we gain new information about the opponent, we could ask the network again.
Okay.
Thank you.
So currently just training it on a large set of a number of matches played by a number of different humans. So if you actually used unsupervised learning to group these first to different playstyles, would that help? Because I mean, currently what you're doing, you can be interpreted as basically constantly, seemingly randomly switching between playstyles. Or did you? Is that the plan?
My plan is just to improve it with reinforcement learning, and I think this supervised learning step is similar to what they did in AlphaGo.
Right.
So I haven't planned to do any.
Okay, but yeah. So, but would you agree that there is no one right playstyle?
Yes.
So wouldn't it be better to sort of try to isolate those game traces that are from a particular playstyle and train only on those to get a more coherent behavior?
So, for example, on good players.
No, but I mean, good. I mean, if you have so obviously I know nothing about StarCraft, so I'm just like spewing random opinion. But games in general, good players typically have a number of different playstyles. And if you train it on a number of players exhibiting very different playstyles, you're going to get behavior that sort of oscillates between these playstyles. So maybe like, doing unsupervised learning on the full data set to try to get playstyles, and then try training on only part of it.
Yeah, that makes sense. If I had a larger data set.
Right? You had a what?
If I had a larger data set, maybe that would make sense, yeah.
Good point.
Yeah.
Any other questions? Okay.
Sorry, we actually have 26 people watching from the live stream now, and somebody has mentioned that if the speakers could just make sure that they're more consistently speaking into the microphone, so like our audience at home can actually hear that. That's also for future speakers. And I'll hand it back to Julian.
Thank you. Excellent talk and very interesting questions. In particular, when Julian mentioned about different playing style, it reminded me our tutorial yesterday about the diverse human players with different playing skills and styles. And actually, to be honest, I've never played StarCraft. I tried to ask questions about it, and I've never played. When I was watching video, I don't know what they are doing. I'm a fan of League of Legends, but when I was playing it, I'm such terrible player, so no one wants to play with me. I can only play with my friends. Well, that may explain why I have fewer friends now. So if people only collect data from very skillful players, they just get us. We need to accumulate the real data from real humans who have different playing style, could be very aggressive or soft, or like me, who want to just destroy the game or our team. Well, I took so much time. Let's thank the speaker again. Thank you. So next talk will be given by Magnus.
Where is mine? Well, I think maybe it's better if the last one is, then okay. I can do it. Yeah. So, thank you, Jalen, for introducing me. This is actually joint research with me and Martin Royakkers, who actually did most of the work. I'm only presenting the paper. I'm also not really a very good StarCraft player. I believe more in Warcraft than in StarCraft. Anyways, my talk will be today on resource gathering algorithms in the game of StarCraft. Frankly speaking, as I said, it's a competition paper and it's not as general as we have seen so far. Anyways, I was planning to tell you a little bit about StarCraft, but I can actually skip this because the previous speaker did actually an excellent job. And then I can dive immediately into the resource gathering. And I'm a little bit afraid, Jalen, that again, quite some time is remaining. Anyways, we focused also on the StarCraft Brood War, the one from 1998. I'm actually quite surprised that we are still working on a game from the 90s. I can still remember when I was a student, my friends started to play this game quite a lot, switching from Warcraft to StarCraft. So I also lost many friends. Jalen, sorry. Anyways, it is a quite balanced RTS game. That's also why it is very popular, also as a research topic. And for those who never played it, Jalen, the goal is you win by destroying the enemy buildings. So, in short, in that case, it's very popular. There are many animal competitions, and since 2014, we as Maastricht University we have our own bot, Letterbot. It always does well in the student StarCraft AI competition, which is organized by the CIG Technical University in Prague. We even won that competition in 2014, 2015, and 2016, and also we won the mixed division. And every time, half year later, if you participate in SIG or 8, we never get further than a third or fourth place. So this is a kind of curse we don't understand. But it also shows that these bots are evolving quite fast. Anyways, as already the previous speaker already indicated, there are many components you could actually focus on, many tasks. I didn't make a huge, nice tree, but interesting ones are, for instance, scouting, because there's a fog of war. How to place these buildings. You can also have all kinds of build orders. We're using also some text mining for that, for human strategies. Also how to compose humans. Also, when you're going battle, you can plan a little bit around. We are playing around with MCTS. We had it in our engine. We kicked it out when our armies became too large for the MCTS to handle. We now are going to integrate it again. And actually, the whole plan was to discuss MCTS, but we didn't make it in time. So therefore, we decided to discuss resource management. And that's actually quite important because the better you gather all resources, the faster you can build a strong army, and the more chance you have to defeat the opponent. In this paper, we will focus on gathering minerals. In StarCraft, you can actually gather two resources. One is so-called gas. but mostly there's only 1 or 2 gas geysers around a base, and you don't need a very fancy resource gathering algorithm. The classic built-in works very well. For the minerals, it's a different story. There are actually many mineral fields, so it's sort of a little bit more complicated. And minerals are quite important because you need it for units and buildings, and they are gathered by the worker units. And the more minerals you can get, the larger your army becomes. So the goal is try to gather as many minerals as possible in a short amount of time. Of course, you can use the built-in, but it's maybe better to actually kick that one out. I will show some results on that. It's actually to improve the scheduling or actually to compute better paths to the mineral field. So the built-in, that's actually the default behavior in brute war. And what it simply does, a worker unit goes to the closest mineral field which is still available. If it arrives and some other worker unit is there, it simply goes to another one. And this is the one used by most bots, and it is not very optimal. What other bots do, and mostly the top bots do this, is actually they distribute all the workers uniformly over all the mineral fields, and they simply tell every worker unit, stay at your assigned mineral field. And because it overrides the default behavior, it every time has to tell a worker unit, please stay at your mineral field. Another approach proposed, and that's not used a lot, is by Christensen et al. They presented this paper actually in 2012 on a multi-agent conference, if I'm correct. And they simply say, well, each mineral field has a queue, where basically the worker units are. And what it does, every time a worker unit becomes available, it computes the waiting and the travel time to every mineral field. And then it simply assigns queues which are belonging to a mineral field very greedy. So basically what it tries to do is to send a worker unit to a mineral field where it can gather as soon as possible the minerals. The only disadvantage with this approach is that you need to have a good approximation of the travel time, and the Euclidean distance which you usually could use is not a very good estimate. So what they have done is basically to pre-compute basically, or to approximate basically how much time it would take from one base to a particular mineral field. We also try to look into the path finding. That's basically a few tricks we employed. The issue is in the StarCraft brute war, it is quite hard to integrate a star. Therefore, we looked to some somewhat faster ways to handle this. So one of the things, what happens in StarCraft, if you go to the mineral field, it goes at a certain moment into gathering mode, and it basically slows down. And we had a kind of trick, is simply we're not going to direct to that mineral field we actually want to go to. For instance, if we want to go to the red ones, we simply go, say, let's go to a mineral field a little bit further. So it will actually move quite fast. It will not slow down because this mineral field is a little bit further. And at the moment you are close by to the mineral field you actually wanted to go, you simply make a small detour. You move around and you go to the red dots. So you could actually, if you do this, instead of going directly to the red dots, you go a little bit further away. Sometimes you have a construction, like the one over here, yes, where it's quite hard, where there are not really mineral fields, so one spot further. Now what you could also do is maybe do the empty space trick. It's simply, if I want to go to this one, I'm not going to do this one directly, but I'm going to the empty space which is behind. And then if I'm close by, I then actually change direction. So I can actually stay out of that gather mode as long as possible, because that actually slows down. The only problem is if you actually not in the gather mode, with this one here, it can actually start colliding with other units. The gather mode actually prevents that, so you have to fix this for the calculate path. So in our co part, we actually are using both strategies. We always prefer the mineral part, because there the collision avoidance is done correctly by the StarCraft engine. For the calculate part, we also have built in some collision avoidance. So all worker units are getting some kind of area where we're not going to pass by in order to avoid collisions. This is relatively computational expensive because you have to check this for all worker units. Anyways, for the experiments, we used the same setup as the one of Christensen et al. From 2012. The same people who introduced that scheduling approach. We used the astral balance map. We started out with one resource depot, 4 worker units, 8 mineral fields, and the gas geysers. And basically, the constraint was that a maximum of 18 worker units were built. And it also built, in the meantime, a supply depot once there are 9 worker units. And the whole setup actually ended after 8,000 frames. We basically compared all these algorithms with each other. So now if you look now into this built-in approach, that was able to gather an average like 4,000 minerals after 8,000 frames. But already that simple mineral lock of actually distributing them evenly in average gave some 500 minerals extra. That gives a huge boost in actually building your army. The more advanced ones, like the queue-based scheduling, gave almost 100 extra, and similar held for co-pod and the co-pod and the combination. But here the differences were actually pretty small. What we also did was to look to a variant of co-pod where we only did this mineral part trick, and that was also able to score like an average like 70 minerals. These are small, well, relatively small differences, but that actually can help you actually building a somewhat larger army in order to defeat the enemy. If you now look to the computation time, that's actually quite important because StarCraft is a real-time strategy game, because in the meantime you want to do something else. We also measured how much time it took over these 8,000 frames to do this build-in. Well, build-in is very cheap. Mineral lock is a little bit more expensive, but it's still quite cheap after 8,000. The queue-based scheduling is a little bit more expensive, but that's something you can still handle. The co-op part actually ate quite some resources due to the collision avoidance. I have to say that the algorithm was not that efficient. What we could have done is actually saying, well, if these worker units were not really in the neighborhood, then don't check anymore. But we actually did the worst case scenario. The mineral part was also relatively cheap. And if you looked at this one, was actually able to score over 4,600 minerals in average. It was quite effective regarding time and minerals gathered. So in the later bot, basically we're using this mineral part improvement because that is giving us the best boost per milliseconds. What I'm trying to tell here is actually that resource gathering algorithms, good ones, they try to improve the path finding and scheduling, and if you're able to do so, then actually you're able to gather more minerals. Disadvantage is sometimes that they take a little bit more time. For next year, I don't know if we're still working on StarCraft Brood War, but that we will switch to the version 2, because version 2 is actually much more interesting, because you can do more stuff. One of the problems we had was to incorporate a star to find better paths. Another one was what we actually want to do is some search look ahead instead of greedy for the queue-based scheduling, because queue-based scheduling also works for StarCraft 2. That's the main independent one. So we will actually switch to the queue-based scheduling because that actually did quite well, as you may see here, regarding time and also resources. So probably we will actually go for the queue-based scheduling. I don't know if the mineral part together with the queue-based scheduling also would work in StarCraft 2. He's now actually looking into this. But for next year, I think we will change a few things. Anyways, thank you for listening.
you, Max. It seems that I can start with StarCraft 2. Any questions?
Thank you for your presentation. And do you have any the data for human players' performance on the resource gathering?
Oh,
Is
good
it-
they are, yeah.
So is it better than the human, or still is far from the human performance?
It's a sensitive question, I have to say. Well, of course, this is a very artificial setup, huh? Because usually you test the winning performance, and we only want to focus how many minerals you gather. And I think if I would give this task a human would be a little bit bored. I don't frankly know, but I know that we could do much more better, because it's still pretty greedy what we're doing here, and also the pathfinding is also not very optimal. So I think machines could do better what they are doing now, but I don't know how efficient humans are. That's a good question. I don't know.
It seems that we are 16 minutes in advance. No questions? Maybe would you like to make...
I can talk about the conference for next year,
Why not?
which will have the StarCraft 2 competition.
This is today's the one where we have the long session, right?
Yeah.
We're actually running a bit short.
Yeah.
For single track questions. I don't think nobody's going to be sad if we're out here today at 6
Yeah.
instead of 6:30. We'll still be out an hour.
Well, okay, because personally I want to support Mark to promote next SIG, but okay. I think
Yes.
now, see, they feel the pressure. They find we may have do a better SIG next year and the next year and the next year. Thank you, Mark. So,
Yeah.
actually, Mark has mentioned that StarCraft is old. It reminds me. Can switch if you want to prepare. Like I just checked on my phone when the Pac-Man game is released. It's first released in 1980. Why I check this? Because recently we get a comment from someone who is not in the game community about the Pac-Man is old game, and doing research in Pac-Man is kind of old-fashioned. This really hurt my heart. We just published a survey about the research around Pac-Man. Yeah, done? Any comment? Yes. Oh, actually, my reaction was, Game Go is much older, right? Yes, it really hurt my heart, and I'm very happy that Alexander Dockham will present his work around Pac-Man today and show people that it's not old-fashioned at all. And I'm very happy it's streaming. Well,
Okay, so hello everybody, and hello also to all the YouTube viewers. And I'm going to convince you that the Pac-Man competition in its current edition is a fresh and new topic and has some exciting new problems. I'm from the same university as Sana, so I need to convince her as well. So, about the contents of this talk, I will first introduce the game for everybody that does not know it, then a short introduction to the current competition challenge, and the previous submissions that were present during previous installments of the competition. Then I will focus on the genetic programming approach and the partial observation, which is a subtask of the current installment. And what I want to propose is the combined coevolution framework. What it is, I will tell you later. Afterwards, I will finish with some conclusions and limitations of this work and present you our ideas for future work. So, what is Pac-Man? For everybody that does not know it, a bit shame on you, because it's one of the best arcade games present. It yielded the second highest cross revenue through all arcade games available. It was only beaten by Galaga, and Pac-Man is the best known video character among American customers. I quickly present you what Pac-Man is about. We have these four individuals in the maze, and the Mr. or Mrs. Pac-Man character tries to clear the maze from all the white little dots and the big white dots. Those are called pills and power pills. Each maze consists of exactly 4 power pills, which help Pac-Man to escape the ghost later on. The ghost tried to catch Pac-Man during that. So Pac-Man scores points for every action he did successfully, so every eaten pill scores him some points, and when the ghosts catch him, he will lose. The problem is, like we already see it here, the ghosts in the first version of Pac-Man are a bit stupid, and they are deterministic, so players found out really fast how to beat them. In the second installment of Pac-Man, the Mrs. Pac-Man version, bots were randomized to make it a little more harder challenge. But however, still humans learned the patterns and tried to detect those early on. So about the scoring function, because it will be an important part of this work, eating one of the pills will score Pac-Man 10 points. The power pills, which make him invincible for a short term, score him 50 points. And when he's invincible, he can eat the ghosts for a short duration. And the first ghost he eats scores him 200, the second 400, then 800, and the last 1600. So it's a very promising strategy for eating the ghosts or for clearing the whole maze. Since it's very risky to eat the ghost, we most often refrain from this and flee from them. So the game ends after no lives remain and the ghosts catch us again, so the final score can be computed. The current version of the Mr. and Mrs. Pac-Man competition versus the Ghost team is added with partial information. So in the usual game of Pac-Man, we have it the left, that we can observe the whole maze. We know the positions of the ghosts and of Pac-Man, and both agent types have a really easy way in finding the shortest path to their enemies. In the partial observation scenario, we have the problem that we only see information in line of sight. So everything that is in our hallway and the site is not blocked by any wall can be get by the API of the competition. Other information will be blocked from us and needs to be gathered in the next ticks. So the hardest task for the ghosts in the beginning will be to split out and find Pac-Man. They have limited communication available, so they can share information, which gives them at least a slight advantage against only partial information by themselves. In previous installments of the competition, we had multiple promising solutions. There were simple state machines, there were Monte Carlo tree search, neural networks, some search algorithms based on ant colony algorithms, and the genetic programming approach. Also, even if it's not handed in or submitted into any of the competitions, Microsoft recently introduced their reinforcement learning solution, which also implemented subtask splitting and tried to use the whole information of the game. However, it is not clear how all those solutions translate to the partial observation scenario. And what I'm going to try to do is to show that the genetic programming approach is capable of generating Pac-Man as well as ghost teams. So genetic programming generates behavior. This is organized as a tree, and this tree contains simple control structures, input nodes, and appropriate output nodes. Evolutionary algorithms can be used to create a diverse set of such trees, and we try to improve the fitness of generated strategies over time. Mutation and crossover can be used to create diversity and also to use usable subparts of it. So in the ghost version of it, we distinguish between function nodes, data terminals, and action terminals. And I quickly want to go through the versions we used. So this was adapted by a previous competition submission, I guess by Atajeli. And the data terminals used are a bit wrapped around the current API, since it only provides us partial information and sometimes we already know some subparts that are not currently available. We created an internal memory for our agent. And for example, is power pill still available can only be answered when we currently see any power pill. But since we know that 4 power pills will be available from the start of the game, we can just count how many we ate, and then we can answer correspondingly. Also, for the most hacking part of this is where are the ghosts, and ghosts have limited movement options since they cannot turn around in an instant. So for multiple ticks we can estimate where the ghosts will be in the next steps. However, after a tick threshold is reached, we will delete this information from our internal memory and don't rely on it anymore. Action terminals are simple API calls that are really provided by the competition. We wanted to have a pure approach as possible, since we wanted to show that from all the information we can gather from the API and all the actions that are available from the API, we can create useful behavior without giving much information into the learning process. So fleeing from closest ghost, going to the closest edible ghost, going to the closest power pill, or to the closest pill are the 4 options integrated into our Pac-Man solution. We tried to validate this by just playing against a simple version hand-coded of the ghost team. And this simple version is shown here with the scoring over multiple generations. We repeated this process multiple times and calculated averages, and you also see some confidence intervals. You can see that there is a slight increase for the best performing individual, and the average performance increases during the first generations very fast, and later on it converges to a certain maximum. We tried to replicate the same for the ghost team, and for the ghost team we basically have the same strategies available in the action terminals, but we needed to add 2 more. Since we had always the problem that after following Pac-Man, but with the 2 Pac-Man option, we were all approaching from the same direction. Pac-Man just needed to collect the closest power pill and turns around, and all ghosts were eaten. He scores a lot of points, and this destroyed the strategy. So what the Mrs. Pac-Man game did was they implemented a ghost that is trying to approach from another side by first splitting from the group and then approaching from another direction. We also added the splitting and the grouping behavior into 2 additional action terminals. Now we also observed how this works. And we had 2 versions of Pac-Man since the API of the game competition already provides those. We used a simple state machine agent and a Monte Carlo tree search agent. Also, we compared 2 additional strategies that were used for creating a ghost team. In the first installment of the Pac-Man game, we have it that a uniform ghost team was created. So each ghost had a distinct behavior, and those were all created with the same strategy. In the Mrs. Pac-Man installment, every ghost had its own personality. So the red ghost was always trying to pursue Mrs. Pac-Man. The blue ghost was always trying to come from another direction. The orange one was trying to guard the power pills. And one was just moving randomly. So we tried both approaches by either using a single evolutionary process with 1 population that is very big, and another one was the diverse version where we used 4 populations and each was distinct from each other, so it can generate its own behavior. But however, it is a cooperative approach since the ghost team always needs to act together, and when the behavior of the first population doesn't match to the behavior of the second population, the scoring will be less. So what we can see here is the evaluation against the simple AI and the MTZS AI. The final scoring is determined by the enemy behavior. So if we are using a simple AI, we can only generate simple counter strategies. But with a more complex Monte Carlo tree search agent, we need a more complex counter strategy, and also he will be likely to score more points when this strategy is more effective. For the uniform and diverse differences, we have that the diverse team faster decreases the score of our enemies. So here are always the points scored by the Pac-Man, and we can see that the Uniform Ghost team started by 6,000 points, and the Diverse Ghost team started by 4,000, even if the total number of generated agents was the same. Nevertheless, we now know that genetic programming was able to create such complex behavior during the generation process, but we always needed to hand code our enemy. And this process is time consuming. It can miss possible strategies like in the simple state-based machine from the Pac-Man version, and it can be limited in the play strength. So what we are trying to suggest is a new framework that is trying to create both agents in parallel, and we want to test if this still works around and what might be the problems of it. So what we used in this competition was the combined coevolution framework. On the left-hand side, we see the single evolution process from Pac-Man, and on the right-hand side, we see the diverse evolution process for the Ghost team. The fitness evaluation is the key point here, since we need information from all 5 populations to calculate the current fitness value. And the Ghost team fitness value will always be dependent on the current playing strength of the Pac-Man and the other way around. So, what were the results of it? The general idea was when one agent type grows stronger, the other agent type needs to catch up. And from our evolution process, we can see that the play strength of Pac-Man was in one generation very high, and in the next generation, the agents already tried to react on this. This process is in the beginning very fast, so we have very short iterations of this process. Pac-Man is very strong, he's very bad, he's very strong again. And later on, this loses some speed. So we wanted to look into it a bit more. But first, we tried if this is a general principle, and here we can see that after multiple iterations of this process, both strategies converge nicely, and the playing strength of all Pac-Man controllers slightly increases, and the playing strength of all Ghost controllers slightly increases. However, we face the problem that both agents lack a bit of complexity in comparison to the single evaluation process, and so we looked deeper into this. And what we got from the insights is that even if it works, but it's incredibly slow, we have loops in this process, and those loops appear in the first generations. After we escape those loops, the evolution process resembles the one of the single evaluation process without hand coding the other solutions beforehand. And to shortly explain how such a loop looks like, it largely depends on the current scoring function used in the game. So in case Pac-Man is currently favoring pills, then the Ghost can freely chase Pac-Man since he won't favor power pills and eat ghosts. However, Pac-Man fastly learns that he is catched by Ghost and he needs some countermeasures for it. So he will eat power pills and pursue Ghosts. Since they are already behind him, he can most often eat all of them and score a lot of points. So the Ghosts need to adapt a second time, and they will now guard the power pills more and more and just wait for Pac-Man to come. Then Pac-Man is again safe to eat all the other pills, and so on. Escaping this loop just takes some time till enough complexity builds up, and afterwards it will just get to another kind of loop. So the open question is how to promote this complexity in the early generations. And first of all, our conclusions of our development process. So genetic programming is also able in the partial observation scenario to generate simple and complex behavior agents. Using 4 diverse controllers was better and converged faster than using only one kind of controllers. Either this is due to generally better to have a mixed team and mixed strategies, or it just needs more time to build the same complexity in a single population. Then the next thing is that combining both procedures potentially removes the need in creating suitable opponents, which is a really huge time saver, and this we want to apply in the final version. But however, the limitations still hold. So we need to, the current strategy development is hindered by those looping processes. And we need measures to detect those loops early on and to promote complex strategies or to escape from those loops. Another point is that those local optimas can be removed by exchanging the internal game score via another fitness function. We didn't look into it yet, but our next simulations all focus on creating another scoring function that is trying to smoothen out the fitness landscape to escape those minimas. And also what might be interesting is if we detect that such a strategy loop exists, then we can maybe employ a dynamic scoring function and remove the influence of one of the parts to promote new strategies. The last thing is that we also want to look into other agent types that we might create with this. And here, for example, we already spoke about creating another scoring function, and this could also be used in a Monte Carlo tree search approach. If you want to look into it, we will update our website on this topic, and you can download all our project files after the competition ended. It may be that it takes 1 more month to produce the final result, but then you can download all our current results and experiments we performed. So this is the end of my presentation. Thanks, and I'm open for any questions.
Oh, everyone. Well, I'll try to be brief. So, coevolution, that loop you mentioned, one way around that is archives, Hall of Fames. You save past individuals and you don't forget things you learn. And another thing you mentioned was how a diverse team of ghosts kind of had a collection of different skills. So I've done some work in Pac-Man, not evolving ghosts, but just Pac-Man. And this whole notion of having separate skills, multiple behaviors, is something I did with neural networks where you can have multiple modes of behavior. And the idea is that you have different behaviors for different situations. It doesn't really plug into the GP framework very well, but it might also be something to look at. But I'll see my...
More or less, we already looked into this. Yeah. We created multiple strategies and then tried to dynamically choose the behavior of it. So we had this archive of strategies that worked during the populations, and then we chose which strategy to apply, but it didn't really help much in the scoring. This might be due to the partial observation that it gives too less information for a decision.
Well, for the evolution, I guess I meant you just keep old individuals around so that the reason the loop happens is because you forget strategies. Or are you saying, but if you shouldn't ever get rid of them, and therefore you should never, like this sort of loop behavior shouldn't really emerge too much.
For the scoring, we used like elitism about the last population. So we always compared against the strategies of the last X generations.
Okay. Well, maybe keep them around for longer. But I don't know.
Maybe. Yep.
So I don't know if you're going to know the answer. Maybe Jacob will know the answer since he seems to have a good library. But I was interested in the bugs that you were finding and whether you'd look to see to what extent humans have those bugs, not just the top players, but sort of novice players too. Because I think, to me, one of the exciting things about AI is when we find things that are true of intelligence in general. So you could be kind of using errors to figure out what's going on with humans.
I only know from the previous installments of Pac-Man, so in the usual versions that are in arcade halls, that humans really maxed out those scores by just finding one perfect pattern and then applying it again and again. But most humans are not capable of doing so. So in the second installation of Pac-Man, the Mrs. Pac-Man, the randomness, even if it's only slightly increased, already hinders most players to detect those patterns.
had a quick comment regarding the loops.
Yeah.
So I did coevolution of tests and controllers before, and there's something like test coverage, where you can actually see whether all the strategies would be checked. So maybe just a suggestion, instead of keeping the last X generations, look at how different the strategies are. So having like a test bed that has more coverage, so more diversity. So that might help. I'm not sure.
We might definitely look into it. Yeah. And Simon? Or Julian?
Question actually relates to the previous things about the Hall of Fame. We have a recent TK paper on looking at transitivities and intransitivities in this. And so this gives you a new sort of insight into keeping the Hall of Fame. It's not just about keeping the best scoring ones, but if you look at how players do against other players in the archive, then even a poor player that's poor on average can be worth keeping if it's good at defeating particular strategies. So by looking at not just the average score, but also which players it's good against, then it gives you a kind of fresh way of keeping the archive.
Yeah, this might be the same.
And it can exactly avoid those sort of strategy loops.
Yeah.
Because you keep it because it's able to defeat that type of behavior.
Okay, this might be another application of this coverage method.
I think so. On the just an interesting point about the human players and Pac-Man versus Ms. Pac-Man. So Ms. Pac-Man, I think the ghosts mostly behave deterministically, following a fixed set of rules, but they have a random location that they aim for at certain stages. So this kind of scatter mode goes randomly, and then they behave deterministically. And some good players, I think what they did, and I'm not sure they ever own up to this, but these strategies, the exact behaviors of the the ghosts, are known because people have disassembled the assembly language and kind of figured out exactly the rules that the ghosts follow. And if you look at people like Billy Mitchell, I don't see the Billy Mitchell interviews about how he sort of sussed out the ghosts and how he feels so superior to them. I sometimes think that actually what he did was to look at the machine code and figure out exactly what they're doing.
So what I read about it was that they changed those strategic points, but the time point is random. And so people that are very skilled in this game can look into this pattern and detect the pattern change then more or less immediately. So, for example, if they switch direction to anything that wouldn't be clear beforehand, then there must be a change and they need the next ticks to decide about the current pattern. So that's what I read about the Mrs. Pac-Man. Yeah.
Okay. And then one more thing, the work that you talked about here, is this entered into the competition tomorrow?
No, because the final points were not enough that we are satisfied with.
Okay.
So, sorry, I can include it now. I just sent it to you.
Okay, thanks.
Okay.
So if you want a single good agent to enter into the competition, what you should do is you take your various best agents from the archive, get a classifier that figures out which type of behavior they behave best against, and make a hyper agent.
This is like the Megabot presented yesterday in multiple versions. So there was in fighting game the Megabot, which just incorporated multiple agents.
Yeah, there's been some. We did some stuff in GVGI. We have a paper from CIG last year about that, on basically selecting GVGI agents that fit particular games. And you could easily do this for particular, where you recognize a ghost team tactic and use classifier to find the right one, which could be interesting to see if it beats everyone else.
I have some time to improve for the next year's competition.
That's very interesting kind of portfolio of agent to play different games or play against different players, right? Any other questions? Like a queue here? No? Actually, I have a question. Could be the last one.
Okay.
Yes.
No,
so very different from the other ones. Have you ever played against your bot?
Yes.
Yes. And how was it?
Since I'm not a very skilled player, the bot completely crushed me.
Okay. You mean you
So
play?
I can only play the Pac-Man variant. I can't control 4 ghost players at the same time. But after a long playtime, it's when I'm choosing randomly from the top generation, then I couldn't really detect one single behavior that is dominating the current generation. Since the genetic programming approach would be deterministic, I included some random numbers, but they shouldn't influence it too much. I didn't find out the pattern like in the original game. So at least for development process, it's interesting that we can create a huge set of different strategies and then just throw the player at it and play against it. And even if we know that he's performing very well against one, we can just choose another one that he's not seeing before.
Actually, it's possible to control the ghost team using this framework. Once I played with Diego, Luga, and another person, we controlled 4 ghosts and try to share the partner. Yes, we were 4. But you can invite Santas to play together and invite other 2 people. And we were kind of yelling at each other, say that the Pac-Man is on the left, you lost it. It was a lot of fun.
Okay, so thanks for all the suggestions.
Thanks for the presentation. Let's thank all the speakers again. Thank you.